Howdy, hi. Pretty good.
Not email. This is great.
People, we made it. We got to the end. And all we've got left is that one little pesky exam. And all I want to do today is help you get ready for that exam. I also just want to point out that Physics 106 is so much more fun than Physics 105. We're going to be doing all sorts of really fun topics: music, wave, electric circuits, magnetism. I've got a levitating track that cost us $7,000 we're going to play with. All sorts of fun things. So I hope that you're going to continue on with this journey next semester. I'll be teaching all of the sections of 106 next semester. There's a morning and then there's a noon class. I retired from Montana State University 2.5 years ago. And I got a call from BYU asking me to come down and talk to them. And when I came down to talk to them, they tried to convince me to help them teach. And I went back and I talked to my dear wife, and we decided that the answer was not no, it was heck no. We had a good life there. Everything was perfect, and my wife just loved Bozeman, Montana. And then, as you know, we made the mistake of going to the temple and praying about it, and now we're here. And I firmly believe for about 3 months after I came that I was doing the good Lord a favor, that he owed me big time for this. And it didn't take long for me to realize that it was the other way around, that he had done my wife and I a huge favor by providing this opportunity. And as I have interacted with you and just felt of your spirit as you come fresh back from your missions, and just the excitement that you have about being here at BYU, it's brought this old man back to life. I was pretty close to burnout, and you have changed everything. So I owe you, and I owe the good Lord for this opportunity. Is anyone willing to give us one last prayer for the semester before we? Oh, okay, Brinley. Thank you.
Dear God, we're so thankful for this semester and for Professor Francis and how much he's shown his love and guidance to us. And we ask thee for a special blessing for finals and just for this holiday, that we might be supported by the Spirit, and we might feel the Spirit and remember Christ in Christmas, but also we might be able to find people to uplift and serve. And we say these things in the name of Jesus Christ. Amen.
Thank you. Okay. We have a review session tomorrow evening here at 7 o'clock in the evening, and I'm just going to answer questions. If you want to come and pepper me with questions to get ready for the exam, I'll record that, I'll post that, I'll send out a link to everyone if you can't make it. I know that a lot of you have evening employment. Let's start. I've got 2 old exam questions here. Where are my helpers over here? Thank you. Any other help over here? Thank you. No. Helpers over here. Oh, the great Britain. Okay. Thanks. If you could give one to him. Yeah. Oh, big.
I stole yours.
We didn't get a chance to talk about angular motion problems in person. It happened on the Tuesday before Thanksgiving, and so you watched that video. But it is an important part of this, thank you, of this part of the class, and it's going to be represented in a big way on that last exam. So we really need to, you know, if you didn't watch that video, you need to go back and watch that video. What we found was that there were 4 kinematic equations for rotational motion that looked exactly the same as the linear counterparts. This is final velocity, initial velocity, acceleration. These formulas should look familiar, and they'll of course be on the front page of your exam. We also had a condition that we called the rolling condition right at the end of that video. And it should be called the rolling without slipping condition. And what we found was that the velocity of the car could be related to the angular velocity of the wheel. And the factor that we needed in there was the radius of the wheel. Now, that's going to come in very handy with this problem here, where we're told that this car is going 30 meters per second in a straight line. And the first thing we're asked to find is the initial angular velocity. And so for part A, we can say, well, since the velocity of the car is equal to the radius of the wheel times the omega of the wheel, this is going to be 30 meters per second. This is 0.5 meters. I'm looking for this. And so that's going to be 30 meters per second divided by 0.5 meters. And that it gives me 60 per second. But that doesn't feel right. And you remember, we can always put in this radian. The radian has no units to it. It's meters divided by meters. And so we can put that in to remind ourselves that we're talking about an angular velocity there. Now, for part B, we're asked what, we're told in the problem that it gets 45 meters down the road during the time that it's stopping. And we want to know what angle in radians does the wheel turn through during this 45 meters. Well, this rolling condition is really 3 equations. Because of the relationship between velocity and displacement and angular velocity and angular displacement, I can write that the distance down the road for the car is related to the angular displacement of the wheel. Again, the factor that relates them is the radius of the wheel. And so in this case, I would have, if I use that equation, I would have 45 meters is equal to 0.5 meters, that's the radius of the wheel, times my theta that the wheel travels through. And that gives me a an angle of 45 meters divided by 0.5 meters. And that's 90 nothing. I mean, there's no units, absolutely none. Meters divided by meters. But I know I'm looking for an angle, and so I can plug that radians in there whenever I need to remind me that I'm talking about an angle. Are there questions about that part so far? Okay, yes, sir.
Will those equations also be on the front page of the exam?
Will the rolling condition be on the, I believe so. I've placed at the map site. I took a picture of the front page of your exam and posted it there, so you can go and see whether it's there or not. It should be. If it's not, I don't know how I can fix it, but we'll figure a way. In part C of this problem, we want to find the magnitude and, oh, wait a sec, we're not ready yet. In part A, we wanted the direction of the angular velocity. Well, the direction of the angular velocity, remember, is given by that right-hand rule. Since those wheels are rotating counterclockwise from our point of view, my right-hand rule, my right thumb is pointing out of the page. And so this omega here is going to be out of the page. Now in part C, we're asked to find alpha, both magnitude and direction. Now, there's two ways you can go about this. One is to recognize that we still have one more equation over here in the rolling condition, and that's that the linear acceleration of the car down the road is related to the angular acceleration of the wheel. Again, it's the radius of the wheel that relates them. So if I just calculate what the linear acceleration is and divide by the radius of the wheel, I could get my answer. But there's another way to go about this, and that is to treat this as a standard motion problem, just like we were solving at the beginning of the semester, where I make my list, always the same list. And remember, these are the rotational counterparts to what we used to have, which was delta x, a, v initial, v final, and delta t. Well, we need 3 of these in order to solve for the other 2. Well, what do I know? I know delta theta is 90 radians. I know that omega initial is 60 radians per second. I know that it stops in some time that we'll look for in part D. But right now, what we're interested in is alpha. And that makes the time the who cares. And remember, that's the piece that tells us which of these equations to use. If we don't know the time, and we don't want to know the time, at least not until part D, I look for the equation that doesn't have time in it. There's time, there's time, there's time. I've got to use this 4th equation. So I plug into that 4th equation. Theta, okay. And so this is 0. This is going to be 60 squared plus 2 alpha 90. And if I solve that for alpha, what do I get? I get 20. Okay, I get negative 20 radians per second squared. Okay, let's talk about that minus sign. Well, just like in linear motion, when I'm slowing down on the freeway, my velocity vector and my acceleration vector have to be in the opposite direction. Well, it's the same thing with angular motion, and that means that my angular acceleration is going to have a magnitude of 20 radians per second squared, but its direction is going to be opposite the velocity, angular velocity vector. So if the angular velocity vector was out of the page, it has to be into the page. Are there questions on how I got that? Okay, yes.
How do you know that it's the velocities into the again?
Oh, the velocity's out of the page, and that's by right-hand rule. We curl the fingers of our right hand in the direction the wheel's turning, and our thumb is telling us the direction of the omega vector. Okay. Remember, we've got two very different right-hand rules. We've got one right-hand rule for omega, angular velocity, and a very separate one for torque. What we don't have, but a lot of people want it to be true, we do not have a right-hand rule for alpha. For alpha, you just got to use reasoning. If you're speeding up, it's in the same direction as omega. If you're slowing down, it's in the opposite direction. Okay? Yes, sir.
I just want to make sure something. So when we talk about circles, are there three different types of acceleration? We could either talk about angular, centripetal, or acceleration that's tangent to the circle.
Well, the tangential acceleration and the centripetal acceleration are both linear accelerations, okay? They're the change in the linear velocity. And that was, we were trying to make that distinction with that homework problem with the glob of gum on the turntable, okay? So essentially, if I've got something on a turntable, the glob of gum, if this is spinning faster and faster, my linear acceleration would have both a tangential component and a centripetal acceleration, which would point towards the center. But the alpha is how much the omega is changing.
Okay, so just kind of one follow-up question to this, because I was getting confused on the homework. So when you ask for linear acceleration, you're asking for the vector sum of centripetal and tangential acceleration.
Yes,
Okay.
yes.
Oh. Yes, the thing I was also confused of is it's like do we only get tangential acceleration if the circle speeds up?
Yes, or slows down.
But isn't that also shown by the angular acceleration sticking out, which also shows if the circle is speeding up or going or slowing down or sticking in? That's perpendicular to it.
So you're saying if I have one of these, do I also have an alpha?
Yeah.
Yeah. But they're one's telling me how much this is changing, and the other one is telling me how much that is changing. But if I've got one, I've got the other.
So there's some sort of relationship between the two, but maybe we just don't go into that.
So this would be the tangential acceleration and the angular acceleration. Okay. Okay, now part D asked us for the part that we didn't care about in part C, and that's the time. Well, again, now I have 4 pieces of information. There are 3 of these equations. 3 of these equations that would give me the right answer for delta t. And when I get more than one choice of equation, I always go for one of these first two that are more basic. And because I just calculated alpha and I might have made a mistake, I think I'll go with this one just to play it safe. You see what I'm doing there? So I would say, delta theta is equal to 1/2 omega initial plus omega final. Delta t, this is going to be 90 is equal to 1/2 60 plus 0. Delta t is going to be 90 divided by 30, and that's going to be 3 seconds. Okay. Now, the last part of this problem asks us to find the mass of the car. And that seems out of place for a motion problem, okay? Because you look at these equations and mass is not in there anywhere. But I do know an equation that has mass in it, and that is, let me just get rid of this here. Newton's second law. Okay. Now, I'm told that the net force is going to be, let's see, I've got weight down, I've got the normal up, and I've got this friction force, and it's going to be that way. And that's a static friction force. And we're told that that's 15,000 newtons. And if I'm calling this direction the positive direction that it's going, that would be a negative 15,000 newtons. I'm looking for the mass of the car. If I had the acceleration of the car, I'd be done. Well, now I can use this last equation here. The acceleration of the car is equal to the radius of the wheel, 0.5 meters, times the angular acceleration of minus 20 radians per second squared, and that's going to give me a negative 10 meters per second squared. So if I plug in a negative 10 meters per second squared and solve for the mass of the car is going to be 1,500 kilograms. Yes, sir. That's given in the problem, right at the last line there.
Oh, the braking?
Yeah, the braking force. Yeah, if since the car's going this way and I want to slow it to a stop, I got to put a braking force this way. And that's by the road on the car. Okay, check on your neighbor. Make sure your neighbor's doing okay. Okay,
Even though I was.
let's talk about buoyancy. Let's turn the page over there.
Good study time.
I had a German professor, an old guy at MIT, and every time he finished filling up a board, 2 grad students would jump up with buckets of water and sponges and immediately start erasing the board. I've never seen anything like it. I need to teach in Germany. Okay. In this problem, we've got 2 blocks that have the same volume. Both of these blocks have a volume of 500 cc's. And one of them's wood, and it's floating with half of it above the water. Actually, it's not water. It's some sort of liquid that has a density of 1.6 grams per cc. So the wood is floating with half of it above the surface and half below. And the metal, we know that if we just put it under the surface and let it go, it has an initial acceleration of 3 meters per second squared down. That's what we're told. And so the first thing we're asked for in part A is the buoyant force on the wood. Well, some of us are still trying to just plug and chug into that formula for the buoyant force. And I'm pretty sure that that's going to get you into trouble. And I just want you to think about what it means, Archimedes' principle, that the buoyant force is equal to the weight of the fluid displaced. If I gave you a bunch of objects, and I asked you for the weight of those objects, really quick, tell your neighbor, just pow, what is the weight of those objects in newtons? If I put them on a scale that measured newtons, what would they weigh? Okay. I hope what you did very quickly was convert this to 0.6 kilograms and then say the weight of that object, the square, was going to be 0.6 kilograms times 10 newtons for each kilogram, and that gives me 6 newtons. And if you do the same thing here, you get 15 newtons. Do the same thing here, you get 4 newtons. That makes sense? I mean, we've been there before, right? Now, if I give you this wooden block has a volume of 500 cc's, but only half of that is displacing liquid. That tells me that the volume of displaced fluid is 250 cc's. Now, if I knew how many grams that was, we just proved to ourselves that we could find the weight of that, right? And hence the buoyant force. Well, the way I go from cc's to the grams is through the density equation. And if I multiply both sides by volume, I get the mass is just the density. That's how many grams I have per unit volume times how many units I have. So in this case, I have a density of 1.6 grams for each cubic centimeter. And 250 cubic centimeters are displacing or pushing out of the way liquid. And so that's going to give me 400 grams. Well, dang, I already did that problem. 400 grams, if I put it on a scale, weighs 4 newtons. And so that means that the buoyant force, if I drew a free body diagram for this, the buoyant force would equal 4 newtons. Does that speak to your soul? You just find the number of cc's that are being displaced. You use this equation to find out how many grams are being displaced, and then you write that as 0.4 kilograms and say, how much would that weigh? And you just multiply by 10 to, well, 9.8, we'll call it 10 to find that. Okay, now this part B asks what's the mass of that wooden block? Well, I know that the weight of that wooden block has to be 4 newtons. Why? because I've only got two forces, buoyancy up and weight down, and it's not going anywhere. Okay? Now, if the weight is 4 newtons, which is equal to the mass times 10 newtons for each kilogram, that gives me a mass of 0.4 kilograms or 400 grams. We okay with that? Okay. So where do we go from here? From here, we want to know the buoyant force on the metallic cube. Is that brutally simple or even easier than that? Tell your neighbor what the buoyant force on the metal cube is.
Sorry.
Okay. Did you get 8 newtons? The two blocks are the same volume. The difference is that the wooden block is only displacing half of its volume, 200 cc's of liquid. But the metal block's completely submerged. It's displacing all 500 cc's. And so it's essentially pushing out of the way twice as much liquid. So it's going to have twice the buoyant force. Yes, sir.
You always give us blocks that have the same volume, or will we have some scenarios where they're different volumes?
I could do anything. Life is cruel. Yeah. But you'll be ready for anything. Okay? You'll be ready for anything. Okay. So in part D, we want to find the mass of that wooden block. And to do that, we need a free body diagram. We've got the buoyant force, which is 8 newtons up, and I have this weight force of the metal that is the mass of the metal, that's what we're looking for, times G. And I also know, we're told in the problem that this is accelerating at 3 meters per second squared. Well, remember, G is just 9.8, we're going to call it 10 meters per second squared. Okay, so if I use Newton's second law, and let's call down the positive y direction since the acceleration is down, I've got the mass of the metal times 10 meters per second squared, that's my weight, minus my buoyant force, and that is going to equal the mass of the metal times the acceleration of 3 meters per second squared. If I want to solve for the mass of the metal, I need to bring all of the terms over to one side of the equation that have the mass of the metal in them. And so I would write mass of the metal times 10 meters per second squared minus 3 meters per second squared. I bring the 8 newtons to the other side and it becomes positive. And so the mass of the metal is going to be equal to 8 newtons divided by 7 meters per second squared, and that's 1.14 kilograms. Okay. Now, the last part of this problem says, what if you had a third block that was made of the exact same metal as this metal block, but it was twice the volume, twice the size? Well, if I go back to this equation, let's see, where am I gonna put that? Let's put it right here. My equation was mass of the metal times G minus the buoyant force is equal to the mass of the metal times A. What we want to know is if I take this block that's got twice the volume, would my acceleration still be 3 meters per second squared, or would it be bigger or smaller than 3 meters per second squared? And what we see is that if we make this block twice as big, I'm going to have twice the mass. And because that is twice as big, it's going to be displacing twice as much fluid. So I'm going to have twice the buoyant force. And you can see from that equation that all of the red 2's cancel out. And so the acceleration is going to be exactly 3 meters per second squared for this third metal cube. Check on your neighbor again. Do a buddy check.
Oh, same density.
It's twice the size.
Okay. Question. Okay, let's do another buoyancy problem. This one is right from a sample exam. We have 3 measuring cylinders and we have 3 different liquids, liquid A, liquid B, and liquid C. We're told the density of liquid B and C, but not liquid A. We're also told that we fill up these measuring cylinders each to 25 milliliters. And then if we put this ball that we have into the cylinder with liquid A, the level rises up to 40 milliliters. We also know that if we put it in the same ball in liquid B, it floats with 2/3 submerged. And we also know, of course, that the ball sinks in liquid A. So talk to your neighbor how you're going to find the volume of the ball. Tell your neighbor how you're going to find the volume of the ball.
Volume of the body bag, and then.
Okay. Well, where that ball is at the bottom of the cylinder, liquid A used to be, had to go elsewhere, had to go up. And so the volume of the ball is just going to be the final volume of 40 milliliters minus the initial volume of 25 milliliters. And that's going to give me 15 milliliters, which is 15 cubic centimeters, which is equal to 15 centimeters cubed. Those are all identical, just different ways of representing the same thing. Okay. Now, in the second part of this problem, we were asked to find the mass of the ball. Now, when you're looking for the mass of something, you want to find an experiment where the object floats. You remember our example of the 10-ton ship floating. Well, it has to displace an amount of fluid equal to its own weight. It has to displace 10 tons of fluid, whether it's in fresh water, salt water, or liquid mercury. Okay, and so if I knew how much liquid B was being displaced, I would know the mass of the ball. Well, remember, I've got this formula that the mass is equal to the density times the volume. So in this case, what I would have is the mass of the ball is equal to the mass of liquid B displaced is equal to the density of liquid B times the volume of liquid B displaced. Well, now I'm stuck. How much volume did liquid B got displaced? Well, we're told that this thing is floating with 2/3 of its volume under the surface. So the volume displaced is 2/3 of the volume of the ball. And that's going to be 2/3 of 15 cc's or 10 cc's. So now I can come back here and say, well, the mass of the ball is going to be 1.2 grams per cc times 10 cc's, and that's going to be equal to 12 grams. Now, in part C of this problem, we're asked for the density of the ball. Well, that's just the mass of the ball divided by the volume of the ball. Well, that's going to be 12 grams. That's what we found here, divided by the volume of 15 cc's, and that gives me 0.8 grams per cc. Now, there's another way we could have worked that. We could have worked this backwards by saying that 2/3 of this ball is submerged in liquid B. Remember the iceberg, that tells us that the density of the ball is equal to 2/3 the density of liquid B. And that's going to be 2/3 of 1.2 grams per cc. Well, that gives me 0.8 grams per cc. Either way, I get the same answer. Do another buddy check. Check your neighbor real quick.
I'm under the volume.
Okay, questions? Yes.
Are we ever need to convert units for these density problems?
Convert units.
Like kilograms, grams, or?
Well, you're always going to need to convert from grams to kilograms before you find a weight in newtons. So you always have to do that. I don't believe on the problem we would ever have a density. I'm sure that we never have a density given in any units other than grams per centimeter cube. Yes, that's the word kilo actually speaks to my students in Montana State University when they're buying a kilo. The BYU students, it doesn't say anything, so sorry about that. But you're healthier. That word of wisdom helps you. Okay. Now, the next question was, if I put this ball into liquid C, is it going to sink or is it going to float? Tell your neighbor real quick. Sink or float, sink or float.
Yeah.
Okay. It's going to float. And that's because it has a density of 0.8, whereas the density of liquid C is 0.85. the ball has a smaller density than the liquid. Indeed, I could even ask you what fraction of that ball is under the surface of liquid C. And that's just going to be 0.8 divided by 0.85, which I think turns out to be like 95% is underneath the surface. Now, the last question is, in which liquid, in which container is the buoyant force going to be the greatest, in liquid A or liquid B? Tell your neighbor what the answer to that is. In which case is the buoyant force going to be the greatest?
Oh, this was used.
So whichever one.
Okay. We know from that last buoyancy problem that if the objects are in the same liquid, if this is water for both of them, the one that has the most displaced liquid is going to have the bigger buoyant force. But that's not what we got going on here. These are not in the same liquid. I mean, it's the same ball, but in one case it's in liquid A, in the other case it's in liquid B. And sure, it's displacing more volume, more cc's of liquid A, but that's not what gives me the buoyant force. The buoyant force is, you know, the weight of that fluid, the weight of that fluid. So what I have to do to make this determination is look at a free body diagram. In liquid A, that ball is at the bottom. I've got a weight force of the ball, and then I've got two forces supporting that weight. I've got a buoyant force due to liquid A, and I also have a normal force by the bottom of the beaker on the ball. Okay? But if I look in liquid B, well, in liquid B, I still have exactly the same weight, okay, of the ball, but now the buoyant force is able to support that weight all by its onesies, okay? So it's going to be greater in liquid B than in liquid A. Questions on that? You have to ask yourself what's the same. In this case, it's the weight of the ball that's the same. In this case, it's the fluid that's the same. Okay, that's what makes them very different. Okay, we've done buoyancy plenty. This still has a little bit of buoyancy in it. This is fun. I love this problem because it combines torque and buoyancy into one problem. We have this meter stick, and it turns out that meter stick is 1 meter long. That's why we call it a meter stick. And we find that we can make it completely stationary so that it doesn't move up or down or left or right. It doesn't rotate. If I hold it with 3 strings, the first string is T1 of 2 newtons down, and the second string is 6 newtons to the right, and the third string we want to look for. We want to know how hard do I have to pull on that string? At what angle relative to the vertical do I pull on that string? And where do I attach it to the meter stick so that this thing does not rotate? Okay? So there's 3 things I'm looking for, the 3 things that have question marks up there. Now I'm told in this problem that the volume of that meter stick is 300 cc's and the weight of the meter stick is 4 newtons. That's given in the problem. Now, the first thing I need to do to solve this is to find that buoyant force. Well, the good news is it's water. It's not oil or heavy cream or alcohol. It's just water. And so water's 1 for 1. 300 cc's is 300 grams. And 300 grams is 0.3 kilograms. And that's going to weigh 3 newtons. Okay. So that buoyant force is going to be 3 newtons. I hope everyone sees that right off the bat. See if your neighbor made that connection.
Right away.
Okay. Now, let's find that string's tension. Okay, and this is one of your homework problems that's due tonight. You're welcome. So what I'm looking for is the tension in 3, the magnitude. I'm looking for the angle that it makes. And I'm looking for the distance from the left end that I have to attach that string. I've got 3 unknowns, so I need 3 equations. And my 3 equations are all the force up has to equal all the force down, and all the force left has to equal all the force right, and all the torque clockwise has to balance all the torque counterclockwise. Okay. Now, that tension is neither all X or all Y. So I'm going to change my my goal. I'm going to take, let me draw this real quick. I'm going to take this T3 and I'm going to break it up into a TY and a TX. Okay. And so now what I'm looking for is TX and TY. And if I can find what those are, I can find this with Pythagorean theorem. And I can find this with the inverse tangent function, right? Just like the old days. So let's go and do this. Let's start with this one. All the force up is equal to all the force down. Well, I've got force up, I've got TY. I've got the buoyant force. And that's it. And down, I've got the T1 and I've got the weight. If I solve that for TY, what I get is TY is equal to 3 newtons. Well, now let's balance all the force left with all the force right. Well, that's really easy because the only force I have to the left is TX, and the only force I have to the right is T2, which is 6 newtons. So I've got that. And that lets me find T3 is going to be the square root of 6 newtons squared plus 3 newtons squared. And theta is going to be the inverse tangent of, let's see, I want the opposite side, which would be Tx over Ty. And that's going to be the inverse tangent of 6 newtons over 3 newtons. Okay? So I'm 2/3 of the way there. I just need to find that R. And to find that R, I'm going to need to balance my torques. And I'm going to balance my torques about this pivot point right there. And this distance here is the R that I'm looking for. Well, if I choose this as my pivot point, T1 gives me no torque. T2 gives me no torque because its line of action goes right through my pivot point. Tx gives me no torque. Remember, it's acting right here and pointing this way. It has a line of action that goes through the pivot point. Now, I do have a buoyant force that has a torque, and I've got a weight force that gives me a torque. So let's balance all the clockwise torque with all the counterclockwise torque. If I pretend there's a great big spike forcing this meter stick to hinge, to rotate about this spike. Ty is trying to make it go counterclockwise. The buoyant force is trying to make it go counterclockwise. The weight force is trying to make it go clockwise. So my clockwise torque is going to be 4 newtons times its distance to the pivot of 0.5 meter. The counterclockwise, I've got Ty times its distance to the pivot R. And remember, Ty was 3 newtons. And then I also have this buoyant force of 3 newtons, and that is going to have a different distance to the pivot of 0.5 meter. And then I just solve that for R. And this is going to be R times 3 newtons is going to be, I've got here 2 meter newtons minus 1.5. That's going to be 1/2 meter newton. And if I divide both sides by 3, I get a distance of 1/6 meter. Check again on your neighbor, please. Good job.
But you can.
Other questions on that problem?
I know that.
Okay.
Oh,
I've had a lot of people ask me questions about this problem, the first problem on the homework due tonight. And so in the interest of time, let me start with that one and we'll see if we have any time for the other one with the pointy headed Greg. That one offends me. Before I erase this, are there any questions on the meter stick problem? Yes. Oh, the pivot point I choose to get rid of any unknowns that I'm looking for. In this case, the meter stick is not rotating about any point. And so I could choose any point as my pivot point. I could choose this point here, in which case I would eliminate these 2 torques. And I would eliminate that torque and that torque. And then I would just have to balance this with that. And that would work just fine. because I was looking in this problem for the distance away from the left end, it just seemed like that would be the simplest choice. But there's no one right choice in this problem. If you've got more than one unknown, then you want to choose the pivot to eliminate the unknown that you don't care about. Okay? Okay, let me erase the board while you're talking to your neighbor and telling your neighbor how you solved this problem in your homework.
Is that type?
Okay,
Like,
let's start with an extended free body diagram of that beam. And the first force that I put on any diagram is going to be the weight force. You're going to have some mass of the beam that's different than 90, but I'm just going to take 90. And so this weight force is 900 newtons. And then we have Will pushing with 400 newtons, and he thinks he's helping, and he's not. Okay, he's not helping at all. Bob and Will are trying to keep that beam from moving, either left or right, or up or down, or rotating. Okay. Now, I also have a roller there, and that's going to give me a normal force on the beam, earth on the beam. Now, I know that Bob is going to have to push this way to counteract Will's push, and then he's going to have to push this way to keep this thing from tipping due to the weight. Okay, and so I'm going to call this the Y part of Bob's push, and I'm going to call this the X part of Bob's push. Bob's push is going to look like that. Is that pretty clear? Now, I know that all of the force left has to equal all the force right. So this force in the X direction by Bob has to be 400 newtons. To find the Y part, since I've got two unknowns, I've got this force by the roller and the force up by Bob, I need to balance torque. Just saying all the force up has to balance all the force down is not going to do it. So since I have two unknowns, and this was your question just a moment ago, how do I choose the point for the pivot? I care about this unknown. I don't care about that unknown. So I choose my pivot to be right there. Now you're saying, Greg, that's where it would pivot. If it pivoted, it would pivot there. But it's not. It's not pivoting about any point. So mathematically, I'm free to choose any pivot point. So I choose it for practicality reasons, not for, oh, it would pivot there. Okay, and now I balance all the clockwise torque with all the counterclockwise torque. Again, I pretend that I put a big spike through that beam right there, forcing it to rotate about that point. Well, this is going to give me no torque because it has no lever arm. This is going to give me no torque because the line of action goes through the pivot point. This is going to give me no torque because the line of action goes through the pivot point. What I get is a torque due to this one that's trying to make it go clockwise, and a torque due to the weight trying to make it go counterclockwise. So the clockwise torque is going to be the normal in the y direction by Bob times its distance to the pivot, 1.5 meters. And that's going to equal the counterclockwise torque, the weight, 900 newtons times its distance to the pivot. And if I divide both sides by 1.5, what I get is the y is going to be 900 newtons times 1/3, or 300 newtons. So you see that the push by Bob is going to have an X part of 400 newtons and a Y part of 300 newtons. You've been here before. That's a 3, 4, 5 triangle. That means the force by Bob is going to be 500 newtons, and this is going to be 37 degrees above the horizontal. Okay. Now, this is the only time in all of history that Bob gets fed up with his brother. Normally, he's very, very patient. But this time, he's just had it. He's just had it. And so he just walks away and leaves Will to support this beam all by his onesies. Okay? So what direction does Will have to push on his end of the beam to make this stay put? Down. Okay? So let's redraw this. I've got a pivot point here with the normal by the roller. I've got the weight here. And I've got the push by Will here. And that's it. And now, if I use the fact that this is 1/2 meter and this is 1/2 meter, if I balance the clockwise torque by Will with the counterclockwise torque by the weight, what I get is that, I'll put it right over here, 900 newtons times, oh, that's counterclockwise. Let's say the normal by Will times 1/2 meter is equal to 900 newtons times 1/2 meter. And that gives me the normal by Will is equal to 900 newtons. Now, here's a fun fact that will come handy on the exam, is that now I can use Newton's second law. If this is 900 newtons, I still have to add all the force up, balance all the force down. And so that means that this normal by the roller has to be 1800 newtons. If I go back to this problem here, all the force up has to equal all the force down. I have 900 down, I've got 300 up. This is only going to be 600 newtons there. Does everyone see where I got those numbers from? Just Newton's second law. Now, folks, we don't have enough time to go and do another problem, but I just want to really encourage you to take that 106 class. It's going to be a lot of fun. And I'm looking forward to interacting with you again in that class. I'm looking forward to continuing this journey together. Good luck on that exam, folks. And remember, I love you. You're not supposed to clap for physics, people. Thank you, though. You're very kind.
Thank you, guys.
Look at me.
Yes. That's the beauty, is that the weight force, we can spread it out over the whole beam using calculus. Or we find that I get the exact same answer if I just pretend it's all at the center of mass. And so, you know, if you're taking calculus, you can do it that way and you get exactly the same answer. Life is sometimes friendly.
Again? Will you take?
It's not for credit. You can watch the videos and everything. It's technically on same person. But they forbid me from.
Yeah, there you go. That's real. That's real.
Water bottle in it. Like your water bottle.
Yeah.
Oh, no, we got plenty of room. Yeah, send me an email. I'll give you an ad code. We got tons of seats available in both sections.
Hey,
Yeah.
Ross, review.
It's quite been gone.
I need a
Right? Everyone's been saying she's dead, and then I heard you went, but now she.
I got home from mine.
No, I have no.
I jumped right into a junior level class and it was so hard.
And help font, they just seen book.
And so,
I forget your.
um,
I thought you were so.
I would encourage,
Are you like?
and you're leaving right away? Yeah, okay. So I would encourage you to at least, before you take 106, skim through some of those videos. That kind of, or maybe probably the better thing would be to just jump into 106 and every time you feel like they're over your head, go look for the video. All of them, every single, yeah. Okay, here you go. Hey, Kevin, right? Oh, man, I'm on a roll.
Let's go to Saturday.
Jackie, thank you.
Oh, yeah. Yeah.
I'm not gonna show that
I see what you're trying to do.
to anyone.
That's too good.
Let's see, for the buoyancy question.
It tastes like peanut butter, but there's.
I want this to drag out, because when I go home, I gotta help my wife put Christmas lights on the roof. I do not wanna do
Okay.
that.
For here, we talked about how the buoyant, oh no, it wasn't that one, it was the second half.
Let me just hit a button here. Oh, no, I'm gonna be there tomorrow morning and next week as well. Yeah.